potential countermass.
Let me join the other speakers and thank the organizers for inviting me to this very nice and exciting meeting. My name is Mohammad Bahramy. I'm from the University of Tokyo and also from RIKEN Center for Emergent Matter Science. And today I decided to talk about some of our recent works on transition metal Weishaupt measurements. In particular, I will talk about some topological phases that we have found in these systems. I apologize for the slight change that I have made in the abstract. The works that I discuss are mostly included in this recent paper that we have published. And my main collaborators in this work are Oliver Clark and Philip King from the University of St. Andrews, and also my very good friend and colleague, Dr. Guang-Yu from Korea. And this work has been just selected as the cover of Nature Material in January's issue of the journal. So we are going to talk about transition metal Weishaupt measurements. And as you all know, in transition metal Weishaupt measurements, we are dealing with these layered systems in which we are basically dealing with a transition metal which is stacked with chalcogen. And therefore, and of course, there are two types of bonding between these atoms. We have interlayer weak type of van der Waals bonding, and then also within each layer we have a strong covalent or ionic bonding between our transition metal and chalcogen. So, in a very rough picture, we can think about two physics. One physics comes from our transition metal d orbitals, or it comes from p orbitals of chalcogen. Most of our studies so far have been dedicated to the d orbitals. For example, we know that when we are dealing with the d orbitals in transition metal dichalcogen, we can think about very exciting physics like spin valley locking, Valley Hall effect, seismic photoluminescence, negative electron compressibility, and etc. And we have little studied the things which are related to the p orbitals, basically because the p orbitals are a bit far from the Fermi levels, and thus the physics may not be so much relevant to the applications. So before starting the main physics, which is related to the p orbitals, and they are actually very interesting in terms of topology, I will just briefly talk about one of the examples of the things that we have, for example, studied for the d orbital in transition metals, and it is basically this negative electron compressibility, which is the effect of electron-electron correlation on the electronic structure of transition metal dichalcogen. As I just mentioned, if you look at, for example, the band structure of tungsten diselenide, you will see that near the Fermi level you have bands which are dominated with the d orbitals. And of course, they have very interesting properties which have been slightly covered in the morning's talk. So what we know is that when you look at the, for example, conduction and valence band, they are pretty much dominated by d orbitals. And interestingly, you have very weak interlayer hopping, which means that our states are not so much dispersed in the z direction or along the kz direction. Because of this, you can think that although you have a bulk system of these layers, still you have your hidden spin polarization. So each layer still keeps its spin polarization. So when you have, for example, a monolayer of tungsten diselenide, you think that your valence valleys are spin polarized. But since you have inversion symmetry in your bulk system, then your system becomes non-spin polarized. But the thing is that this spin polarization is actually hidden within each layer, but they are kind of reversed, altered from one layer to the other layer. So you can think that actually in the bulk of this system, you can still have a hidden spin polarization, which is opposite from one layer to the next layer. And this is, for example, have been confirmed by ARPAS measurements by my colleagues in St. Andrews universities. And you can see that, for example, when you do the ARPAS measurements, you can see that from one valley to the other valley, the sign of the bands, the spin polarization of the bands is reversed. For example, here is positive and then it becomes negative, and it is the opposite for the other k value. So this is something that we know, and it is very interesting that you can reveal this. You can have something which is hidden in the ball, but then you can, of course, since it is like a spatially localized spin polarization, you can think that you can make a quantum confinement near the surface to reveal them. So if you, for example, do band bending, or chemically you modify the electronic structure near the surface, you can reveal this hidden spin polarization. And this is something that, for example, again, our colleague has done for tungsten diselenide. This is, again, you can see that the electronic structure of pristine tungsten diselenide, where we have our k values. And then when you start to slightly dope the surface by some kind of alkali metals like rubidium, then you will see that you slightly have some kind of splitting at the k values. And then, of course, you have some little pockets at the conduction part. But one thing which is very interesting is that if you look at the trend of band bending, you will notice that as you increase the amount of dopants near the surface, the conduction band starts to go to lower energies, but your valence band starts to raise. So you have two different trends of bending. For the conduction part, the bands are shifted downward. For the valence part, the bands are shifted upward. And of course, the chemical potential appears to change by increasing the dopants near the surface. But this change in the chemical potential is not like what you expect from a normal band bending. For example, in the case of normal semiconductors, or say topological semiconductors like bismuth selenide, when you have band bending, then what happens is that when you have band bending, you see that both conduction and valence band are equally shifted downward. So the band bending happens for conduction and valence band in the same way. It's not like one band shifts upward, the other band shifts downward. So this trend of band bending seems to be different in the case of tungsten diselenide. So here it appears that we cannot consider a conventional band bending mechanism. We need to go beyond that, and we need to think about something which requires a non-interacting picture. So since you have d orbitals, and these d orbitals are subject to electron-electron interaction in the case of tungsten diselenide, the kind of band bending which conduction bands experience is different from what valence bands experience. And this is very interesting. Then, in order to explain this, we use this Landau theory of Fermi liquid, in which when you include the interaction, this interaction requires that your Fermi level, your chemical potential, be modified by the amount of charge that you put in the band. So, for example, in the 2D and 3D case, you can see that this factor, which is called compressibility, in the case that you don't have any interaction, is always positive by changing the Wigner size radius, or say this Wigner size radius is basically the distance between your carriers. So when you have more carriers, Wigner size radius becomes smaller. You can see that when you have no interaction, they are always positive, which means that you have a positive compressibility, and that means that you put more carriers, your chemical potential shifts upward. But if you include interaction, interestingly, at some limit, it becomes negative, which means that you have a negative compressibility. In a very simple sense, it means that when you put more carriers, your chemical potential shifts downward instead of shifting upward. And this can be, for example, shown with this animation, right? If you have a non-interaction system, when you put more carriers, your chemical potential shifts upward. When you have interaction, the chemical potential shifts downward because your bands are modified due to this electron-electron interaction, which leads to this negative electronic compressibility. In order to include this, then we did some kind of RPA calculations, and by doing RPA calculations, we could treat the conduction bands in a different way that valence bands are treated. And then you can see that when you do an RPA with a finite thickness treatment, then you can basically reproduce the experimental data as you can see here. And then we have this program which solves the near surface band structure by combining Poisson equation with our Schrödinger equation using a tight binding scheme, and then using this self-consistently, you can see the effect of band bending near the surface. By doing this calculation, then we are able to basically reproduce this opposite trend of change in the conduction and balance band, and this is what I have shown here. You see that when we increase the carrier density, basically the balance band raises up, and the conduction band starts to disappear due to the band. So this is one interesting example of D bands of physics in transition metal Dirac. Now let's go to the case of P bands. For the case of P bands, basically what we have found is that actually you can have some kind of protected, symmetrically protected Dirac cones and also topological surface states. So when we talk about Dirac semi-metals, when we have this kind of Dirac phase, basically we are going to talk about Dirac semi-metals. You all know that graphene is the most famous Dirac semi-metal, where we have these Dirac cones at the corner of the Brillouin zone, and they are basically protected, and they are there, and they are fourfold degenerate due to the inclusion of inversion and time reversal symmetry. Recently, there have been some reports about some other Dirac semi-metals, like cadmium arsenide and silicium bismuth, where you still have these beautiful Dirac cones at some arbitrary k points along AL direction, gamma A direction here, and then when you do the arcs, due to the presence of these topological Dirac cones, then you will have two Fermi arcs connecting the Dirac points from here to here. And the appearance of these two Fermi arcs is exactly because we have a fourfold Dirac cones in our bulk. So you have one Fermi arc here and the other Fermi arc here, which include these Dirac cones to each other. So these are things that we know that you can have very interesting topological Dirac semi-metals, but we still don't know much about the stability of these Dirac cones and how they can be stabilized in a bulk system. So in the cases where we have inversion symmetry and the time reversal symmetry, if we just rely on our basic knowledge of topological phase transition, what we know is that if you have some kind of tuning parameter, like pressure, like temperature or whatever, when you change this tuning function, you go from a normal insulator to a topological insulator, and this transition happens at a critical point, and this critical point is shown here. And then this critical point is basically unstable. You can move from one point to other point, but it is always one critical point. If you break inversion symmetry or time reversal symmetry, this single point can be shifted to a range. So you can have this Dirac semi-metallic phase ranging from two critical points, M1 to M2. And then here, of course, you can have while semi-metallic phase. And this is something that we know. So either by breaking inversion or time reversal symmetry, you can stabilize this. In the first case where we break inversion symmetry, for example, this is one case where, for example, we apply pressure on bismuth telluride iodide, which is a non-central symmetric system. We can clearly see that we have a transition from a normal insulator to a topological insulator. And by going to the topological phase, you can see that we will have this surface states here. And then it follows this beautiful, simple phase diagram where we have this central region where we have a Dirac semi-metallic phase, and we will have a while nodes in the system, in the bulk system. But again, we are talking about an inversion and time reversal symmetric system where both symmetries are present. And we are going to say that how we can stabilize a bulk Dirac semi-metallic phase in a range of parameters, like here from going from M1 to M2. So in order to do that, what we know is that we need an additional symmetry to be included in the Hamiltonian. So what we have found is that you need, for example, rotational symmetry. If you have rotational symmetry in addition to inversion symmetry and time reversal symmetry, then basically you can describe your Hamiltonian, your 4x4 Hamiltonian like this, and each block can be described like this. Now, since we have rotational symmetry, our Hamiltonian should commute with a rotational operator as well, like this. And then, of course, we will have a rotation axis. Let's say that rotational axis is our KZ direction. Then, basically, you can simplify your Hamiltonian and decompose it like this along the rotational axis. This is, for example, considering that KZ is our rotational axis. So by doing this simplification using our Pauli matrices and Pauli pseudo-spin matrices, then what you can do is that you will realize that in order to satisfy all conditions, basically due to the presence of time reversal symmetry and inversion symmetry, which requires the double degeneracy of the states, then among these D1, D2, and D3 factors that we have here, only one function can be non-zero. Otherwise, we cannot satisfy these two conditions. And then we also know that we have non-spin polarization, which means that all bands should be spin degenerate. Then this means that D1 should be 0. And it simplifies our function like this. So our Hamiltonian can be simply decomposed like this. And since we have one function and two parameters to tune, then this means that you can have a range of pressures or parameters within which you can establish this Dirac semi-metallic phase. And this is, for example, the phase diagram that you can draw to show that how this topological Dirac semi-metallic phase can be realized from M1C to M2C, which is our critical parameters here. This is what we have known. And then going back to our transition metal dichalcogenide, here we already have a rotational axis. For example, here we have trigonal symmetry. In many of these systems like iridium telluride, palladium telluride, and other wanted transition metal dichalcogenide, we already have a rotational axis. And then what we have now is that we have two chalcogen, one chalcogen here and the other chalcogen in opposite, in kind of inversion symmetric point in the layer. So what happens is that you can now look at this system in this way. Let's think that we have two chalcogens which are located at x1 and x2. And just look at the p orbitals of these chalcogens, okay? Now what happens is that we think about these chalcogens far from each other. When you think about this and you bring them close to each other, you create bonding and antibonding for the p orbitals of your chalcogens. So you have something like this. Now, since we have a crystal field symmetry due to our trigonal axis, then what happens is that your p orbitals will be split in terms of their symmetry, like this. So basically, you have either pz or pxy bands for both bonding and antibonding part. And now, if you include a spin orbit coupling, then your bands will have a double representation like this. And since you have two chalcogens which are located at different locations, the parity of the bands will be like this. So it will be either plus plus minus or plus minus minus. So this is very interesting. You can have a change in the parity for one single orbital manifold. If you just think about p orbitals, they should all have same parity. But since you have two, then you can manipulate the parity in this way. So now let's look at our gamma and n, which are located on the rotational axis. And then what happens is that since you have this Bloch wave factor, phase factor, then you will have this change in the dispersion on going from gamma point to A point. Let's think about the PZ orbitals where we have the strongest interlayer hopping between the orbitals, and think that you have no hopping between the PXY bands because they are in plane, and you are thinking about KZ, which is out of plane. So you can basically see that naturally you will have this kind of dispersion on going from gamma point to A point. So you will think about two crossings between this branch of the band with this branch of the bands. But the thing is that just one of them is symmetrically protected and the other one is not protected, and it will be gapped due to the spin orbit coupling, as has been shown here. And the reason why it is gapped is that these two bands have the same symmetry character. You see that it is R4 and this is R4 as well. So here it will be gapped out. But these two bands have different symmetries. This is 4, this is 5, 6, so they cannot be hybridized with each other. So you have protected crossing between these bands. And interestingly here you see that wherever you have the crossing between the bands, you have also an inversion of the parity. So the sign of the parity changes from minus to plus or plus to minus. That means that it is a topological band inversion, which means that you should have a topological surfaces here. So you can have both a protected crossing between the bands, and also you can have a topological band inversion within one manifold. So this is very interesting, and they are symmetrically protected also. So this is the total picture that you can draw for any transition metal dichalcogen which has a trigonal symmetry. And then when you think about this picture that I showed you, here I assume that these bands have no dispersion, but in reality you can have dispersion for your PXY type bands. And since this dispersion is controllable, then you can think about either type 1 Dirac cones or type 2 Dirac cones. So depending on the slope of the bands, either you can have a type 1 Dirac cone or a horizon, which is a kind of threshold between type 1 and type 2, and eventually a type 2 Dirac cone. So everything is controllable here. This is one example, for example, for palladium ditelluride, where we have done the band structure calculation, and you can already see that you have these protected Dirac cones along gamma n direction, and also you have this topologically inverted band gaps here. And when you look at the surface of band structure, you already see that you have either a topologically non-trivial surface state, or you have these bulk Dirac cones. And then one more thing is that actually you can have both type 1 and type 2 Dirac cones in the same system. So when we compare our calculation with the Arcus measurements, we can clearly see that there is a very good correspondence between the calculation and experiment, and the experiment confirms that indeed we have this kind of Dirac semi-metallic cones, Dirac cones, and also topological surface states, or a range of materials, which has been shown here. And also we have done this theoretically for some other systems, and we already see that this is really a general trend. You can have type 1, type 2 Dirac cones, and also we can have topologically non-trivial surface states. And since, of course, we are talking about Dirac cones, then it means that at the surface you should have some fermions. And already we see that for the case of iridium ditelluride, when you look at the surface projection, you can already see that there are two fermions which connect the bulk Dirac points to each other. So to show that indeed we don't need any d orbitals here to stabilize these Dirac cones, I have, for example, shown the case where we have excluded the d bands from the case of palladium ditelluride. So this is the ab initio band structure, and this is a toy model in which I have removed the d orbitals. Already you can see that in this toy model you still have the band crossing, protected band crossing between our p orbitals along the gamma a direction. And also to show that how we can tune the type of the Dirac cone, I have made another toy model, a simple type binding model. So here we consider all possible hoppings between our chalcogens. So here you can think about in-plane hoppings from each layer, X1 channel or X2 channel. And also you can think about two different kinds of hopping from X1 to X2, or interlayer hopping from between the layers. So you can think about two different kinds of interlayer hopping, which have been shown here, like T3 and T4. And thinking about sigma bonding and pi bonding, then we can basically think about different scenarios. This is one scenario where we consider that we have T1 equal T2, the hopping for the planes are the same, and then for interlayer hopping, I assume that there is a very big interlayer hopping within the layer, so T3 is 0. And then I just change the T3 pi like this. So you can see that by tuning the hopping parameters, you can have either a trivial semi-metal, or you can have just a type 1 crossing between the bands, or by increasing the T4, then you can have a type 1 plus an inverted band gap here. And eventually you can have type 1, type 2, and inverted band gap. So if we also include the interlayer hopping, for example, if I assume that I have this finite interlayer hopping from X1 to X2, then I can have even more rich phase diagram like this. I can assume that in this case when T3 pi is constant and I change the T4 pi and T4 sigma, then I can have type 1 in this range, I can have type 2, I can have type 1 plus inverted band gap, I can have type 2 plus inverted band gap, and eventually type 1 plus type 2 plus inverted band gap like this. So we can even have a topological insulating case at this energy range like this. So by tuning these parameters, you can have very rich topological phases in a single in a single system with trigonal symmetry. And this is just a summary of the phases. One more interesting thing that I just want to show you before concluding my talk is that when you have the case of a system where you break inversion symmetry but still keep the rotational symmetry, you can still have these protected crossings along the rotational axis. So remember that we say that if we break inversion symmetry, we should have wild nodes, not the Dirac nodes. And that's because we break inversion symmetry, right? But if we have rotational operation in the system, and if this rotational operation is like what I described for you, then along this rotational axis, even though the system has no inversion symmetry, still you can have protected Dirac crossings. So you can have protected crossings which have fourfold degeneracy. So this is something kind of counterintuitive finding, that you can break inversion symmetry but still have symmetrically protected Dirac cone in a system. And this is, for example, one example that I showed you, that I show here to you for a system like palladium, tellurium, silicon, where we break inversion symmetry, all the bands are spin polarized, but still you can see non-spin polarized and symmetrically protected Dirac cones along gamma A direction. So with this, I'd like to conclude my talk, and we have shown rotational symmetry can realize null topological phases in transition metal dichalcogenides, and these Dirac cones observed in these systems are solely from one single orbital manifold, and there are p orbital manifolds. And finally, by controlling the interlayer hopping, we can realize a very rich range of topological phases, like type 1, type 2 Dirac semi-metallic phases. Thank you very much for your attention.
Questions? Yeah.
So your elementary unit can be either T-type or H-type.
Yeah, you're right. Yeah.
As long as you just need C.
Yeah, we just need a rotational symmetry, and it doesn't matter whether the arrangement is T-type or H-type.
Thanks for interesting talk. And I got one question for the first part, the negative compressibility. Now, when you put in the electron interaction interaction, the RPA every calculation, that's the standard free electron gas type of calculations. Just wondering, because for NX2, the conduction band edges and valence band edges are all major d orbitals.
Right.
Okay. So, so the correlation in d orbitals may be different from the correlation effects in the free electron gas. Does that matter, or I mean, or your answer seems to be the results seem to be quite good, surprisingly good.
No, actually, as you can see, I probably showed you here. We consider, of course, an ideal free electron gas, but as you see, actually, if you do that, you don't get a good correspondence between agreement between the theory and an experiment. Yeah. So you see that if we just consider an ideal two-dimensional electron gas, then actually the agreement is not that good. We need to consider a finite thickness, and for this finite thickness, we need to apply the RPA definition. Otherwise, it's not possible. So this indeed shows that the thickness of the electron gas plays an important role. So you cannot consider that you have a kind of ideal.
And the finite thickness is for the trilayer, the whole thing.
Yeah. But since they are d orbital, you can just imagine that it happens at the center of each layer.
At the center of the d orbital at the center of each layer, but the last curve, I mean the solid curve, including the thickness of the trilayer, including the
No, here we assume, since we consider Bahramy functions, then the Bahramy functions are basically localized on the transition metal, so we don't really do that. Challenges.
Concerning this Palladium tellurium seminar,
Yeah.
you said that even though you break spatial inversion symmetry, you still have a Dirac point. But I would guess, even at the beginning, this Dirac point is not due to inversion symmetry, but maybe due to some mirror symmetry or threefold rotation symmetry.
So this protection, you see that happens along gamma, where we have this rotational axis. So actually, this rotational axis plays somewhat, here rotational symmetry plays the role of inversion symmetry.
Yeah, so when you break inversion symmetry, it will still be there.
So this is somehow, it compensates the breaking of inversion symmetry by having this constraint that you put on this axis, because this is the rotational axis and this is the special axis.
Okay, so that's fourfold including spin. Is it?
Yeah.
Thank you very much for the nice presentation. I have a question about Schrödinger equation. Could you go back to the slide? Okay. So here in this case, how did you couple with DFT?
So we use maximally localized Bahramy functions to take the block wave functions from ab initio. So we take those orbitals which are interesting. For example, in the case of Taiwan, we just look at those bands which are related to the conduction and valence band near the Fermi level. So by downfolding those bands, we then can have a simple tight binding Hamiltonian. And then what we do is that from the Poisson equation, we will find a new on-site potential, and then we couple this on-site potential with our tight binding Hamiltonian. And then from this tight binding Hamiltonian, you will get a new charge density. And then this charge density will be used for the Poisson equation to get new solution for the potential. So this goes self-consistently until you find.
So though in Poisson equation is like a charge density, electronic charge density. You got it from DFT function, wave function.
So it comes from DFT, and then it will be modified through this loop that you have.
So,
and of course, we need to also have a treatment for the dielectric function.
Okay. Okay, thank you. Thank you for your great presentation. And I want to ask about, you mentioned about type 1 and type 2 Dirac point. And like type 1 Dirac point, there's some chiral anomaly or some transport property. So is there anything about type 2 Dirac point?
So of course, since in the case of type 2 Dirac point, since the slope of the band is different, then basically they will have some consequences on some of the observable parameters that you have. Like let's say that on your thermal conductivity, on your CD, I forgot the term for it, and our heat capacitance and other things which are related to the thermodynamics of the system. And also, the thing is that now we are considering, with my colleagues in Osaka University, we are trying to see if by changing the things from type 1 to type 2, whether we see a change in the Bahramy phase as well in the magneto resistance. When you have these SDH oscillations, then basically you can somehow extrapolate these fan diagram, and then you can get the Bahramy phase. So according to the measurements, apparently there is some kind of change in the Bahramy phase between type 1 and type 2. So we are now trying to see whether it has something to do with the dispersion of the bands, which is different between type 1 and type 2.
So this type 1 and type 2 are near the Fermi surface, so you can see.
Yeah. For some cases like iridium ditelluride, you can tune them to be near the Fermi level.
So you have already seen SDH oscillation for type 2 semi-metal.
I haven't seen, but my colleagues apparently they have seen something for hearing that already. We are still analyzing it.
Okay, let's thank the speaker again. Next talk will be given by Professor Zhang Taizong from National Chuang University. And his title is Electronic Structures in Topological Semi-Metals and Its Structures from Basic Principles.
Good afternoon. I'm Taiwan Zhang from National Chuang University. First one, I thank organizers' invitation, give me an opportunity to share our recent work here. I'm going to talk about topological semi-metals and discuss the heterostructure in topological insulators. At the beginning, I will very briefly introduce the basic concept and the practice of topology in condensed matter system, and then I'll give an example, a typical topological insulator is Mohammad, and I also discuss its heterostructures. In the second part, we'll focus on semi-metallic phase. Okay. We'll discuss the three typical topological semi-metal, wire semi-metal, nodal semi-metal, and our recent works type 2 Dirac semi-metals. Because the previous speaker has have given a very nice and clear introduction, here I only use a simple picture, recall the key concept. Okay. Even the physics is not precisely, but very simple. In math, we are used to discussing topology in real space. We can recognize the system topology by using this Gauss-Bonnet theorem. We don't need to go to detail. This theorem gives us a G value. Okay. G value equal 1 means there is a hole on the object. G equal 0 indicates there is no hole on the object. So the same G value represents the same topology even their geometry are completely different. So here is a famous example. A topology of a coffee cup is the same as a donut but different from the parabol. In physics, we are familiar with the band structure. So the topology is in momentum space. Okay. Here is an example. There are 3 bands. We can see the band geometry. Okay. The band geometry means the band shape or the band gap size. The band geometry of band 2 and the band 1 and band 2 are almost the same. However, their topology are different. For band 2 and band structure, they look completely different. However, the topology is identical. Okay. It seems counterintuitive. Okay. Let's focus on band 1 first. We can see from the valence band, it's mainly contributed from the b orbital. Conduction band is from the a orbital. For example, a orbital is bismuth, b orbital is selenium. Because the valence band or the conduction band are contributed from one species of orbitals, so the wave function on this band is a smooth function. For band structure 2, okay, most of them from b orbital. However, at this point, it shows a orbital character. So it seems there's a hole on the band structures. So the wave function on this band is not a smooth function. This is why the topology of band 1 is different from the band 2, because the whole number on the wave function are different. In this case, we can see the valence band and the conduction band exchange their orbital character. Okay. We call the band inversion. Band inversion that the system violate chemical bond order and induce the topological phase transition here. Okay. In single particle frame, topological phase transition must accompany band inversion process. similar to the Gauss-Bonnet theorem, mathematically, we can use a mathematical quantity to distinguish topological phase. The terminology is a topological invariant number, which is a random integral of the Berry curvature. If the wave function is a smooth function, this integral equals 0. If there is a whole wave function, which can provide non-zero Berry curvature, so this integral give us integer values. If n equals 0, it is a topological trivial phase. Non-zero n is a topological non-trivial phase, for example, topological insulators. Here I introduce a very important property in topological materials. Topological phase guarantee possesses a gapless surface state on the system boundary or the system edge, and this surface state must connect valence and the conduction band. Different from a typical semi-metal, its surface state can be removed. For example, we can apply external field or impurity absorption. The surface state in topological phase is very robust. Small external propagation cannot destroy this surface state because which resulted from a bulk topology. And most important thing is this surface state is the only measurable quantity to judge the topological phase in experiments. So I say the gapless surface state is the hallmark of the topological phase in topological materials. Here I summarize the key property of topological phase. First one is robust. If one state can continuously deformation to another state without closing gap, make a inversion, their topology are identical. Even their geometry are entirely different. For example, we can continuously deformation from this band structure to this one. Okay. So their topology are identical. It was impossible from this state to this state without closing the gap. Second is we can use the mathematical quantity to distinguish topological phase. For example, we have a two number, lead to index, equal to number, and so on. Third is the gapless surface state. Here is an example. Here's an example. Please see this panel. The flat band, okay, these flat bands are the box states. These two linear lines are topological surface states. Now I artificially increase the spin of the coupling. You can see the band geometry change very dramatically. However, the surface state still survive here in the gap connect valence and the conduction band. Until we make the band inversion, change the bulk topology, the surface state disappear. Okay, this was Sun-Yet. Updated data were from Hassan's group. In updated spectrum, there are two linear lines around the Fermi level, and there is a electron pocket across the Fermi level. This panel is our theoretical simulation. Comparing with RPS and theory, we can easily recognize these two linear lines are the topological surface states, and this electron pocket is the bulk conduction band. So if we theoretically make a band inversion, okay, surface state disappear. Okay, here I give an possible application in topological insulators. Traditionally, if we want control on and off in electronic devices, we need to apply the large current or the gate field. But this kind of setup is cost higher energy and the response is very slow. The next generation devices need a faster, smaller, and energy saving. So one possible way is to develop a spin basis transistor. We can use a rush bar effect to flip the spin to control the on and off. So if we want to control, to flip the spin splitting value is a crucial point. Larger splitting value can reduce the device size as well as using in room temperatures. So there are many previous work trying to make a large spin-based splitting. One of the approach is we can make a heavy metal on a semiconductor heterostructure using its potential gradient to induce spin-based splitting. But in this kind of systems, we can see the splitting is very, very small, and rush bar parameter is also very small. Recently, we found if we put normal metal on topological insulator, normal metal thin film on topological insulator, the quantum wave state will interact with surface state of topological insulator and induce a very large spin band splitting in the metal quantum wave. And our theoretical prediction, the rush bar parameter is around 2 orders larger than the typical semiconductor case. Another case is a bismuth bilayer on the bismuth selenide. In this work, we collaborated with Professor Huang Longjun from National Tsinghua University. His group used hydrogen etching to make a large and uniform bismuth bilayer on bismuth selenide. And this one is their RPS data, and this is our DFT simulation. Our simulation shows in the bismuth bilayer, there is a large spin band in the bismuth quantum wave state. And the rush bar parameter is very large, which comparable with other large rush bar parameters. So the surface state of the topological insulator can be used to induce large rush bar splitting, which may be useful in future spintronics. Topological material is a very large research field. Not only topological insulator, bismuth selenide, there are other topological class. For example, topological contour insulator, big topological insulator, and topological crystalline insulator. Recently, a part of the research have shifted from the insulating phase to the metallic phase. So in next section, we'll focus on 3 typical topological semi-metal: Dirac, wire, and nodal line. This is a wire semi-metal. The bulk band in wire semi-metal is an energy with 3-dimensional graphene. Linear band dispersion from a wire node in all momentum directions. This is RPS data, and this one is our simulation. These are linear band structure signal, and this is a wire point. And wire points can provide non-zero Berry curvature in momentum space, so it's an energy with a magnetic monopole in momentum space. And its surface state, is a Fermi arc. We know the Fermi surface in normal metal must be a closed 2-dimensional shell for normal metal. But in wire semi-metal, its a surface state is an open curve, which connect 2 wire nodes. in this panel, this black and dark points are the wire node, and these bright lines are the Fermi arc substate. Okay, we can see the Fermi arc starts from one wire node and in the end at other wire node. So it's an open curve, and this is RPS data. Okay, because of this unusual electronic structure, so we can expect wire-cell metal not only fundamental physics, but maybe possible future applications will differ from normal metal. However, the wire-cell metal real material is still very rare. We only have a Haas family, but this family has many limitations. For example, Haas is a three-dimensional crystal, so it is very hard to make thin-film in experiments. And previous previous work, both wire-cell metal is an intermediate state between the normal metal and topological semi-metal. So if we can move the wire point, we can study this phase transition. But in task, the wire point cannot be tilted, so it is impossible to explore this phase transition. So our goal is to try to search the wire phase in their structure and try to search tunable wire semi-metals. In 2016, we noticed a tungsten telluride. Tungsten telluride is a layer structure here, and this is bulk band structure. But unfortunately, tungsten telluride is insulated. There is a gap here. The gap is very, very small, around 1 millielectron-volt. So this result implies us even tungsten telluride is not a wire metal, but very close to the phase transition boundary. If we can find a way that B2 and B3 band cross, okay, we can get a wire phase in tungsten telluride. So after our systematic study, we found if we can artificially reduce the spin of the coupling or the lattice constant, we can let B2 and B3 band cross to get the wire phase. But the spin of the coupling is a native quantity in nature, so how to reduce it in experiments? So our solution is multi-doping. We found multi-doping can reduce the spin of the coupling as well as the lattice constant. So this is our bulk calculation in this doping system. These 2 points are the wire points, and you can see a linear line here, and these 2 points are these 2 points. More interestingly, we found the distance of these 2 wire points can be modified by changing the multi-doping concentrations. In this panel, the horizontal axis is the multi-doping concentration, and the vertical axis is the wire point distance. We can see the separation increase as increasing the doping concentrations. So this is a tunable system. We know the wire metal is a topological state, so it's very robust. The only way to kill the wire phase is let them touch in momentum space. Okay, we can give up the wire phase. So the distance between the wire phase can be regarded as a topological strength in wire metal. For example, in our doping system, in low doping region, the separation of the wire point is very small. So this wire phase is delicate. If we increase the doping concentration, the separation becomes very large. So this wire phase becomes robust. We also study the surface properties. This is our surface phase wave simulation. The shaded area is the bulk state, and bright lines are the surface state. These 2 points are the wire points, and these bright lines connect 2 wire points is a Fermi arc surface state. This is K and KY map, clearly shows a Fermi arc connect 2 wire points. So a conclusion of this work is we found this doping system is a wire metal in layer structures. And this system is a tunable system, so which maybe offer a platform to study topological phase transition in real materials. I think because of the time, I skip the experimental part here. The other class of topological semi-metal is nodal line semi-metals. Different from normal metal, which Fermi surface shows two-dimensional features. Nodal line semi-metal, the bulk Fermi surface is a one-dimensional loop in three-dimensional grain zone. So this is a nodal line Fermi surface. The simplest nodal line is a crossing point of two paraboloid bands. So things are very simple. However, this kind of bulk Fermi surface has yet been found in real materials, even in DFT material prediction tables. So we would like to search this kind of loop bulk Fermi surface in real materials. Okay, we notice a layer tangent selenide. In these structures, it's a layer structure. This system lacks inversion symmetry, but has a mirror symmetry along the z-axis. And this mirror plane play a crucial role for protect nodal line. Okay, this is a bulk band structure. It's quite complicated, so we only need to focus around H point. H point is the corner of the hexagonal grain zone. Around the H point, the main contribution is from lat p electron-like band and tantalum d orbitals. They cross each other and form in nodal line. Okay, these crossing states are the nodal line. And this is a KSKY map. It clearly shows a two closed loop at the corner of the grain zone. In other materials, because the spin-off coupling break the SU2 spin rotational symmetry, so most of crossing state will get out. But here we have a mirror symmetry and AHL plane, display AHL plane, just on this mirror plane. So these crossing points are protected by the mirror symmetry. This is why the spinor coupling in our case cannot destroy the nodal line bulk Fermi surface. Okay, this is a surface spatial wave simulation. Okay, this is our simulation. The shaded area is the bulk projection, and the bright lines are the surface state. But because the surface state is very close to the bulk projection, so please see this schematic here. These colored dots are the nodal point, and the white line is the surface state. We can see the surface state connect two nodal points or the merge in the bulk. So this is the signature of the topological band structure. Here I show some of our ARC data. We know the nodal lines are formed from the closing points of lat p and tantalum d orbitals. Okay. This is our ARC data, which successfully capture these properties, capture these features. Okay. This is lat p orbital, and this is tantalum d orbitals. If we remove the lat atom, become a tantalum selenide, we can see the lat electron pocket disappear, so it's empty. Another evidence is this surface state we label SS2 here. Okay. This surface state is from nodal point, from the nodal line below the Fermi level. Okay. So others also again successfully observe this surface state. So combining with our theoretical prediction and our test, we demonstrate that tantalum selenide is a nodal line semi-metals. We also predict other compound. TTS is also nodal line semi-metals. The final one is we have discussed the wire and nodal line, so the final one is a Dirac semi-metal. Dirac semi-metal is very, very rare. Okay. Only NS3Bi and C3S2 are demonstrated by experiments. Okay. We only have two materials. Here I predict, sorry, I forgot. Oh, here, DAL3. Okay. In this compound, it's a symmetry along the Dirac point exists on the rotational axis. The Dirac point is protected by C4 rotational symmetry. Okay. This is a bulk band structure. It's almost an insulator except some discrete point. Okay. It shows a linear band dispersion here. And we found this band structure is highly anisotropy. This is a normal Dirac semi-metals. We can see the slope side of lower cone are upside in Kx, Ky, and Kz direction. But in our system, the slope side of lower cone are upside along Kx, Ky, but along the rotational axis, the slope side are the same. Okay, so this is a type 2 features. If we put a Fermi level on the Dirac point and plot a Kx, Ky map, we can see electron pocket and hole pocket just touch at the Dirac point. This is a signature of type 2 semi-metals. And we also check a topological invariant number. Okay. According to this classification table, we found our system is distinct from the C3S2 and NS3Bi. In these two systems, their topological invariant number are to the Z2 equal 1 or the Milch number equal 1. In our case, it's a Milch number equal 2. So the Fermi arc are two pairs. Okay. This is NS3Bi, it's one pair of Fermi arc, but in our case, it's two pair. Okay. Consistent with the topological invariant number. And Dirac semi-metal is very interesting because it can be read as a critical point in topological phase. It means we can realize different phases just simply break the symmetry. For example, if we break the C4 symmetry, the system becomes a crystalline insulator. If we apply the magnetic field, break the time symmetry, it becomes a wire semi-metal. So because of time, let me skip over the part and go to the conclusion. Okay. By using a DFT and a Taiwan model, we can predict new topological materials or provide theoretical interpretation for experiments. In this talk, we have discussed the tunable wire semi-metal, nodal line semi-metal, type 2, Dirac, and heterostructure in topological insulator. I thank all collaborators, including ARPES, Symbol Growth, and theoretical support. Thank you very much.
Questions? Yeah. Who is first? Okay.
Okay, maybe a quick one. You show us a large brush bar effect on isthmus on topological interior surface along one direction.
Yes.
I just wonder, is the Fermi surface, Fermi level cut through this brush bar Dirac point?
No. The Fermi level is here.
Above the Dirac point?
Yes. So the brush bar spin splitting band slightly above the Fermi level.
And any other band, or this is just only brush bar band across the Fermi level?
If in the isthmus quantum will stay, only brush bar splitting stay here.
No other conduction band?
Other conduction band at the first quantum quantifiable layer of isthmus selenide. So it's not in the
business.
yes, yes, yes.
Professor Zhang.
Thank you. I was just curious about this tungsten telluride case stoked by molybdenum. Okay? And so in the calculation, you have to do supercell calculations and vary that X concentration. So when you do the supercell calculations, you would have different symmetry or different type of supercell. And then at the end, you have to compare the band structure with the original 1x1 tungsten telluride band structure.
Okay.
Does it matter what kind of supercell symmetry and how did you get this band dispersion in your finite?
Thank you. Very good question. Okay. In this work, we didn't use a supercell. Okay. We construct a one-year typing model from that selenide and Marley pendulum, and we linear interpretation between the two hopping parameters. Yeah. And fortunately, our result consists with with experimental data quite well. So this method is work in this case.
More questions? Yeah.
Thank you for the talk. And I think for type 2 Dirac, there's a type 2 Wang-Sen method, I think in 2013 or 14. So can you give some comments for some difference in type 2 and type 1? Or thank you.
Here, we also study random label. Okay. In a Wang-Sen method, the lowest random label state is a chiral state. In a type 1 case, the lowest random state is consists of two chiral states with upside chirality. But here in our type 2 case, we have two chiral states, but the Fermi velocity are the same sign. So now if we apply a magnetic field perpendicular, for example, along a pz direction, so the Fermi level, the electron cyclotron motion will within a KSKY plane. So in semi-classical picture, electron will trace the Fermi surface within these planes. Okay, so now if we apply magnetic field along this direction, okay, the Fermi surface is a closed loop. Now if we tilt the magnetic field like this, the Fermi surface will distort. Now if we at a critical point, the Fermi surface will become an open curve. So all the random label collapse. So at this case, the carrier density will very, very high. So we can observe this effect in experiments.
Also, maybe you will see some
some
SPH or maybe even
yeah,
some
exactly.
from the label. Okay.
Yes.
Just one short question. You have mentioned the nodal line below Fermi level, and so could you comment on its conduction property contributed by this nodal line below Fermi level?
Sorry, we have not considered this effect very seriously. Yeah, but I don't have an exact answer, but simply I can expect this will very different from the Dirac system. Because in the Dirac system, it's very easy to define a random label. But in the cross type of Fermi surface, I don't know the answer, sorry.
Yeah.
An extension to the previous question on the MO doped portion. Okay. So you mentioned that you used a simple tight binding model, and then that fortunately matched with the experimental results, right? Now, is there a predictive approach, as in suppose you take a supercell, what kind of symmetry supercell would lead to this wild semi-metal phase? Or do you have to perform explicit supercell calculations to predict that this would lead to a wild semi-metal phase?
Okay. Because as Professor Zhou mentioned, the supercell method may break the symmetry. So we only test some special value, for example, 25% doping. It consists with our linear interpretation method, and we only use this method in other topological insulator systems. Yeah, again, fortunately, it consists with experimental data. So we guess in the maybe 5D or 4D system, and without strong correlative effect, maybe it's a good approach to study the doping system.
In this particular system, previous studies have shown that for molybdenum dichloride, the lower energy wild node is very unstable compared to the upper one. So if you slightly change the crystal parameters, the lower energy wild node appears to be kind of destroyed. I'm wondering, when you do this kind of interpolation from tungsten dichloride to molybdenum dichloride, do you see any change in the stability of either of these wild nodes or not?
Okay. Actually, this system is this system is a tungsten telluride system. Is a very sensitive system. The separation of the wire points or the number of wire points is very sensitive to the lattice parameter of this system. So we have checked lattice constant from different experimental data, and we found in some systems, moly telluride has 8 wire points. In some experimental lattice constant, we only get 4 wire points. So it's very sensitive on the lattice parameters. So in this system, we choose 8 wire points in moly tungsten telluride for doing the linear interpretation.
Okay, if you have more questions, you can grill the speaker at the break. Okay. We have refreshments and drinks outside. But please come back by 3:50. Thank you.